Hello Year 11. Today we're going to do resolving forces. I'm going to take you through sort of the PowerPoint, and then I'm going to take you through the worksheet. So there are two sections to this. I'll tell you more as we go along, but please feel free to skip ahead of the explanation if you understand this and go straight to the task. But if not, here is today's work, resolving forces, and I'm just going to go into the PowerPoint, which is just here. Now, some questions for you. Hopefully we can remember these. I'm going to skip past them because you can do this in your own speed. Now, if you look at this diagram, this is a car on a slope. We can see 4 different forces acting on this car, and it can become confusing because they're all acting in different directions. They'll all be different sizes. Now, we like to talk about something called the resultant force. What we're doing essentially is adding up all these forces and consolidating them into one force that kind of represents all of them added together. So it becomes a lot simpler. So here, this is what we need to know. The resultant force is where all of the forces acting on an object can be replaced by one single force that has the same effect as all of the forces acting together. That is literally just me saying you get all those forces that look really confused, and you sort of make them into one force by adding them up or taking them away. Now, if we look, let's have a look at the forces that are acting on this stationary car that's on the road. Now, I always start with weight. If you are on a planet or near a planet, you will have a weight. Your weight force will always act directly down. Because this car is on a road and it is not falling through the floor, it is sat on the road, the reaction force must be equal to and opposite the weight. These forces are balanced. The car is not moving, so they must be equal and opposite. Now, this here, because this car is stationary, the resultant force of this will be 0. If I got the weight and the reaction and added them up together, they would cancel each other out. There would be no arrow whatsoever because the car is completely stationary. Let's do a different example. The resultant force. We've got 2 forces that act on a straight line. The car is driving, so let's call the one on the right hand side. Okay, let's call this the driving force, or the pushing force. Let's call this the air resistance, or the drag. Okay, let's draw them. Let's write them on, just so that we. So let's have a little look. Right, this is my my push. This is the drag. You are allowed to use the term drag instead of air resistance. This is the technical term that pretty much catches all. So if you're not sure, drag is probably the best term to go with. Now, so there's my push, 400 newtons to the right. My drag is 100 newtons to the left. My resultant force, well, if I say that this way is positive, okay, this is the forward direction, you can kind of see that this one and this one, they act against each other because they're opposite. So what I get is my resultant force equals 400 newtons take away 100 newtons. So my resultant force equals 300 newtons. Okay, and because this is a positive number, yeah, it's going to the right. So that is my resultant force. Okay. Now, let's do the resultant force on these diagrams, just so you get the idea. So let me just get my pen ready. Okay. Let's do number 1 here. So this will be number 1. I've got 600 newtons pushing to the left. So here's my person. 600 newtons pushing to the left. Sorry, the right. 200 newtons pushing to the left. Let's say that in all of these diagrams, this way is the positive direction, and we'll say that up is also a positive direction, just like you'd have on a graph. If I had a graph like this, so this would be my x and this would be my y. I would say that these are the positive numbers and anything on this side would be a negative number. We'll just do it the same to keep it simple. So here this is a positive, we're pushing to the right, pushing to the left for 200. So you can kind of see, well, 600 and the 200 fighting together, that'll be about 400 and it'll be going to the right, won't it? Yeah, so your gut would be correct, but we should do it mathematically. So we'll call this resultant 1 equals 600 take away 200, and that equals 400 newtons. Again, let's look at this one. Number 2, the same thing again. Well, we've got resultant 2 equals 800 take away 500 equals 300 newtons. And we know that this is also pushing to the right. Sorry about my wonky arrow, that should be straight to the right. This one's a little bit more complicated. Well, we'll do this in 2 parts actually. I think it'll be easier to do in 2 parts, so we'll do this 3. So our resultant force for 3 is going to equal, well, again, this is the positive direction, isn't it? So this is 800 minus 700. And we can't do anything with this 200, because if you look here, this one and this one are directly acting against each other. This one is not. So resultant 3 equals 100 newtons to the right, but it also has a force of 200 newtons going up. So if I was to draw my person, there's my person, and I was to draw the resultant forces on him, so there he is, I've just drawn him over here for number 3. Well, he's got, don't do that, got 100 this way, and he's got 200 that way. Now, in maths you would do it as a vector, so I'm going to combine those two, okay, and it would be 100 that way, 200 that way, so my resultant force would be like that. Okay, we'll get onto that later. For now, this is good enough for now. Let's have a look at this one. So number 4. Let's look at horizontal straight away. So horizontal, so resultant 4, and we're just looking at the horizontal. Well, we've got 800 newtons going to the right, and we've got 800 newtons going to the left. So luckily for us, that cancels out, makes it 0. That's easy enough. We have got 50 newtons going down and 100 newtons going up. We said up was positive, so we'll do 100 newtons take away 50 newtons. That equals 50 newtons. So the resultant for 4 is 50 newtons going up. Okay, because remember the horizontal one cancelled out. This might look a bit complicated now because I scribbled a lot of stuff on this PowerPoint, but you've just got to make sure you only look at the forces that are pointing directly at each other or directly away from each other, the opposite forces, and you ignore the ones that are not. So in this last one here, I had to do it in 2 stages. So we're going to ignore that because I've just gone through them all. Here is a definition that we need to know. If there is a resultant force, it causes an object to accelerate. Now, acceleration involves speeding up, slowing down, or changing direction. If something speeds up, slows down, or changes direction, it is accelerating. If it is accelerating, there is a resultant force. If the object is not moving, or moving at a constant speed, so that is in a straight line with a constant speed, there is no resultant force. Okay? And that's really important. If there is one thing you take away from this lesson, it is this slide. You need to know this. Now, I'm going to leave vector diagrams for now. We will do vector diagrams next lesson. You can have a little sneak peek if you want, but you should do them in maths. I'm not sure if you've done them yet. I'm going to go on to the next bit. So I'm going to get rid of this. And we've got a little worksheet and then an exam question. So, which of these following ones are vector quantities? Now, hopefully we are okay with this because we did this last lesson. And on the right here, we will do, so we'll do calculate the resultant forces for some of these. So let's do this one. So we've got, my pen ink needs to be something that is visible. There we go. So let's do this. We'll do this one. So it's got 6 newtons. We've got 6 newtons that way. We've got 3 newtons going down. What's the resultant force? Well, let's look at the horizontal first. So we'll do horizontal first. Well, 6 newtons to the right take away 6 newtons to the left, because remember we say this is positive. Well, that equals 0 newtons. So there's no horizontal resultant force at all. But let's look at the resultant force in the vertical direction. And again, we'll say that that up is positive and right is positive. We've got 3 newtons pulling this object downwards, but there is nothing pushing it upwards. So the resultant force is going to be minus 3 newtons. Because remember, we said that this is the negative direction. So what's our overall resultant force? Well, it's going to equal minus 3 newtons down. So if I was to draw that on a diagram, you would just have one force, 3 newtons in that direction. So that's the first one done. Let's have a look at this one here. So I'm going to draw my box again. I have got a force going that way for 3 newtons. Now again, it doesn't matter if the force comes to the middle or points inwards, it's still the same thing. We've got one force there that says 4 newtons. We've got one force there that says 2 newtons. Notice how on the diagram the arrows are shorter depending on the size. So let's do the resultant force. And we're going to do it just in the horizontal direction. And actually, there is only the horizontal direction for this one. Well, anything that's going to the right, we're going to say is positive. So we only have one thing that goes to the right, and that's the 3 newtons. And anything that's going to the left, we're going to say negative. And these 2 arrows point to the left, so that is minus 4 newtons and minus 2 newtons. So what does that equal? Well, that should be minus 3 newtons. So what that's telling us is we've got a force going to the left. So if I draw this, my minus 3 newtons, you can draw it like this if you want to, seeing as that's how it was done on the diagram. This is the resultant force. What happens is, these 2 forces here, cancel this force out completely, and you've got 3 newtons of force left over. So you can draw it like that, or if you want, you can draw it like this, which is exactly the same thing, 3 newtons. I'd like to have a go at the other ones. This is just a repeat, so don't do the ones at the bottom. I'll delete them before you get on. Now, another one I'd like to try. This exam question. Give me a second to open it up. There it is. What I'll do, you should pause. You should pause and have a go at the exam question. Once you are done, or you get stuck, you're going to unpause. I'm going to help you through it. Okay, so for now, you're doing it by yourself. So I'm going to assume you've paused, you've had a little go, I'm going to carry on. The diagram shows the horizontal forces acting on a swimmer. Now, I don't like this diagram. As a physicist, I like to draw circles and squares only. So I'm going to draw a little circle here, and there's my swimmer. And it says that there is a T force going this way, and there is a D force going that way. The force T is 120. Okay, so I'm going to write that 120 newtons. They've said that this guy, or this swimmer here, is moving at a constant speed. Well, what does that mean? Constant speed. Speed equals a 0 resultant force. Okay? We've got 0 resultant force. Well, for there to be no resultant force, then this force here must be completely cancelled out by another force. We've only got one more force, D, so it has to be the same, because these two forces will be equal and opposite. So, by increasing the force T to 140 newtons, the swimmer accelerates to a higher speed. Let's draw a new diagram. I'll do this one in blue. Let's do this. There's my... So here I've got... So far I've been told that this is 140 now. This is T. Calculate the initial size of the force. Okay. Well, D, because they're just saying it's the initial resultant force, well, this is still 120, isn't it? So, well, you do 140 minus 120, and you should get the resultant force is 20 newtons. Even though the swimmer keeps the force T a constant at 140, the resultant force on the swimmer decreases to 0. Explain why. Well, that's interesting. So what they're saying is, there's my swimmer. He keeps this force here, T, at 140 constantly. But over time, this force increases, which was the drag force, to be 140. Now, this makes sense if you think about whenever you've been on a bike or whenever you've been in a car. The faster you go, the windier it kind of feels, or the faster you go, the harder it is to run faster or pedal faster because of drag. So, as you get faster, the drag force increases. Well, this person accelerated, didn't he? That means he's getting faster. So, as you accelerate, your speed increases. Yeah, so your speed goes up. And as this happens, as speed increases, the drag force that's force, F-O-R-C-E, the drag force increases until it is equal and opposite. There. So then that's the first point. This is the second point here, until it's equal and opposite, and then this is the third point, until you are at a constant speed again. Granted, this constant speed will be faster than the other one because you are pushing harder, but you will still be stuck at that constant speed until you push harder. Okay. A sports scientist investigated how the force exerted by a swimmer's hands against the water affected the swimmer's speed. The investigation involved 20 males and 20 females, swimming a fixed distance. Sensors placed on each swimmer's hand measured the force 85 times every second over the last 10 meters of the swim. The measurements were used to calculate the average force, average speed of the swimmer over the last 10 meters. So the swim was also measured. Let's have a little look. That was a lot of information. So we're looking at how the force, okay, and the swimmer's hands affected, yeah, the swimmer's speed. That's what they were looking at. Well, 20 males and 20 females, that's pretty important. I'm going to put that green because I think that, to me, sounds a little bit like a control. They swam a fixed distance. Okay, again, stuff that you're keeping the same or you are controlling, I'm going to put in green because that is a control variable. So what I would write in the exam is either, I would probably write something like same, and then same here. And when you get later on, if they ask you about control variables, anything that you've written same next to is your control variable. So they measured the force 85 times every second over the last 10 meters of the swim. Okay. I guess this could be. And I suppose this could be as well, but we'll leave that one out because we're getting too many greens. The measurements were used to calculate, okay, so they calculated an average force. And they measured, okay, hold on, the word measure there. They also measured the speed of the last 10 meters of the swim. That's quite important, the word measure. So they measured this. The average speed was measured. Okay, the force on the person's hands, okay, that was measured. So what was the dependent variable in this investigation? We should know now that an independent variable is something that you change. You should know that a dependent variable is something that is measured. Now, it says, what is the dependent variable in this investigation? The easiest way to figure this out, because this is quite a complicated one, right? The dependent variable, okay, the dependent variable will always be on the y-axis. So if you get your highlighter and you just highlight this one, that there will be your dependent variable. So here it is the average speed. So if you don't get given a graph or a table, you have to work this out for yourself. But if you are given a graph or a table, your dependent variable should always be on the y-axis. Now, explain the advantage of measuring the force 85 times every second rather than just once or twice every second. Hello. Just a quick note. I made the classic error. So it says here for this question, so I'm going to cut the video because I made the classic error. Explain one advantage of measuring the force 85 times every second rather than just once or twice. I said increasing accuracy. Now, that is not allowed. The answer is a little bit more difficult than that. What is the advantage of taking more readings? Sorry, what is the advantage of taking readings 85 every second? Well, the first advantage is you actually have more readings. I thought that was implied in the question, but it's not. So you get more readings. And more readings is always better. If you were asked how to improve an experiment, you would take more readings and you would take an average. That is the answer that you give. And to expand on this, and the word was underlined in the mark scheme. I think it's a bit harsh. So I believe you would probably get more accurate in the real thing. But just to make sure that we line up with the mark scheme, you need to say you've got a more reliable average. Okay, you've got a more reliable average. Another reason why it's good to take a lot of different readings, because when I said that you could take the peak force, what you'll find is if you were to take the strength curve, which is what it'd be called, of your swimming stroke, you would find that your strength curve would start off, so here's my force, okay, and here's my time. It would start off kind of low, and it would probably do that, right? That is a huge range in readings. Now give one way that the data for the male swimmers is different from the female swimmers. Okay, let's have a look. Here's male. We'll do male in blue, like this. The male data is pretty much all there. Okay, and we'll use green for the females. The female data is pretty much all here. Let's have a look then. Well, I can see that the males pretty much mostly, on average, produced more force. You see the average force? They produced more force. Okay, so there's one way that the male swimmers are different, and actually that's probably the best one because they're quite similar everywhere else. I mean, on average, the males could swim slightly faster, but it's only by a bit, and the top male, the top female are very, very close. So I like to say that males produced more force. Considering only the data from this investigation, what advice should a swimming coach give to swimmers who want to increase their average speed? Well, they need to increase. If they want to go faster, they've got to push harder, right? If they want to go faster, they need to increase the average force that they can push the water on. So they could, well, there's loads of things. I think they just want you to say that pretty much word for word. But if you were going to do that in real life, you'd have to train. You could do strength training. You could do technique training. So you need to increase your average force that you push with. And then you're done. Now that you've done that, give yourself a little mark, send it over. Hopefully my explanations helped a little bit more with what the answers are, because I know looking at a mark scheme isn't really that helpful. So give me an email with your work, and I'll see you tomorrow.